All right, shall we get started?
I think so. It's past 2:30, yeah.
Okay, so welcome back, everyone. Let me just quickly share my screen just for a recap of where we are in the tutorial. So we covered part 1 and part 2 in terms of the introduction and the DeepONet. And now we're moving to part 3 and part 4. So heading down the black diamond slopes might not be the best idea since we just had lunch. But thankfully, we have Jacob that has been doing a fantastic job in explaining even the most difficult topics very clearly. So I'm just going to hand it over to him to talk about Fourier neural operators and more specifically the Fourier neural operators. So let me stop sharing and Jacob, you can take over.
Thank you, Paris. Okay, so now at part 3. In part 2, we talked about the DeepONets, which is proposed operator learning architecture that we came across. And now we're going to discuss an alternate way to formulate an operator learning architecture. The Fourier neural operator is built off this idea of the neural operator. This is an idea that came out of Caltech. Again, both of this and the DeepONets are really very recent architectures that have come out in the past couple of years. So for the DeepONet, we kind of motivated its construction by this result of Chen and Chen in 1995, where they were able to come up with this universal architecture that was provably able to approximate any kind of continuous operator between two spaces. And then we used neural networks for the two components of that architecture. We're effectively approximating some finite dimensional subspace that we hope is very, very close to the true image of our operator. But in this section, we're going to take a bit of a different approach and kind of start from the point of what happens in deep learning for normal finite dimensional maps. And so as many people might be familiar with, the simplest kind of neural network architecture that you would learn about getting into deep learning is this idea that we're going to iteratively compose linear and nonlinear mappings. And this is the deep in deep learning, is that we do this a bunch of times. We get a long architecture of linear pointwise nonlinearity, linear pointwise nonlinearity, the neurons and the connections between the neurons literally. And that this kind of architecture ends up being very, very expressive, very powerful, and relatively easy to train. And as we know, it's been proved many times over in a few different ways that this is theoretically universal from an approximation theoretic point of view. With a deep enough network or a wide enough network, some combination thereof, we will be able to approximate any continuous map between finite dimensional spaces. So we might be motivated to say, we want to form a really flexible class of parameterized operators to learn the correspondence between input function and output function. Why don't we try doing the same thing? And the most immediate application of this is, well, we could apply it just to the output space of the first function. Let's consider the case where the domains of the input and the output function coincide, just to say calligraphic x is equal to calligraphic y. And we could literally just use a multi-layer perceptron standard neural network on the target space of the input function. And this does give a well-defined operator between a space of input functions to the space of output functions when calligraphic x and y are the same. But we can pretty quickly see that this is not going to be a rich enough class of functions. And it's somewhat clear to see why this is the case. That's because this is only operating pointwise on the outputs of the function. So, we used an architecture that was from the finite dimensional case, just acting pointwise on a target space. So this is exactly what this is going to do. This doesn't take into account any information about the curve at all. It just looks at a particular output point and it transforms that output space into another space. So for example, if I had two curves that intersected at a point, like I say, I have one line, this is one input curve, I have another input curve this way, and they cross at an x, at the point that they intersect, where those two curves get mapped to, will also have to intersect at that point, because this is a purely pointwise transformation. So it doesn't take into account any global information about the curve at all. And so surely this we shouldn't expect that this is going to be powerful enough to approximate operators that otherwise might be looking at the entire curve, and it might send two curves that intersect to two curves that don't intersect. That's not going to be possible with this kind of pointwise transformation. So we need to add some other ingredient into this linear, nonlinear layered composition, which we will still try to do because we know in kind of standard machine learning, this does work well. So the question is, what is the appropriate analogy of a layered nonlinear linear architecture for operators? And so one thing that you might immediately notice is that on function spaces, there's a much larger class of linear transformations than just linear transformations acting on the output of these functions, which is to say pointwise operations. We might consider those purely local linear transformations of functions because they only depend on the value at that one point. But we have much larger classes of linear transformations. For example, if we take a continuous kernel on the input location space of the input function, again, recall that an input function u is going to be a function from, let's say, calligraphic x to some r to the du. We can take a kernel on the domain of the input function u and convolve u with it. So this is sometimes referred to as an integral kernel transformation. And you can see immediately this does give a well-defined linear map on the space of continuous functions as long as this kernel is continuous. Because I could, give a u1 plus u2 here. Integrals are linear, so this will split into two pieces. Scalars pop out of integrals, and this is a well-defined linear map. But for kernels that aren't, delta functions, I can't represent this as a pointwise transformation with some matrix. And this is a kind of transformation that only appears when we look at function spaces this way. This isn't something that we really see in finite dimensional spaces, at least not in this formulation. So surely we should include this extra structure that we have of linear transformations on function spaces in our layered architecture that we want to propose if we have any hope of it being expressive enough to capture all the sorts of behavior of mappings from input functions to output functions. Interestingly, there's actually another motivation for using this kind of kernel integral transformation, and that comes from the theory of linear PDEs. So consider some kind of linear partial differential equation. L here is some linear differential operator, some mix of partial time derivatives, maybe some partial space derivatives, but that acts linearly on this input function u, and it should equal some other function f. You can think of this as maybe the Laplace equation or maybe the heat equation. And the operator learning problem for a PDE like this would be, we effectively want to learn the inverse of this differential operator, maybe subject to some boundary conditions for it to be well-defined. So if you give us some right-hand side of this, we apply the formal inverse of our linear operator to it, and we get the solution operator. There are cases where there's something called a Green's function, and the Green's function will allow us to find this answer by convolving it with the right-hand side. So we actually know for a fact that there are operators that we might be interested in learning that have exactly this form and nothing else. So we really have very strong motivation to include this as a module in our layered architecture if we want to be doing learning between function spaces. Are there any questions here? Okay, so this motivates the architecture of the so-called neural operator. And the idea is we're more or less going to emulate exactly what happens with normal multi-layer perceptrons, your standard feed-forward neural network, but we're going to include this extra kind of linear transformation that we're allowed to make on spaces of functions, with the hope that then this gives sufficient expressive power to model any kind of operator that we would want. What we talked about in the beginning was if we ignore this part and just look at this, it's not going to be enough. But by including this integral transformation, we're kind of tapping in to the additional structure of the function spaces and the kinds of transformations, continuous transformations we can make on them. We still will allow sigma to be a pointwise nonlinearity. You certainly could come up with crazy complicated nonlinear transformations of functions, but we actually will stick with the very simple form for the nonlinear part, especially since we're going to compose multiple layers of this over and over again, similar in spirit of deep learning. What's interesting about this kind of architecture is that whatever measurement points you have of your input function, this part is being applied pointwise to them. So that part doesn't care what those are. But there are many ways to compute this integral, which we'll talk about in the next few slides, many of them of which will accept different measurement schemes you might have for the function that you're putting in here. This kernel is something that we're going to learn or design ourselves, so we'll be allowed to evaluate it anywhere. We'll only have access to this at some measurement locations, but because we're writing this as an integral, it will be very flexible with respect to where those locations are. And in my opinion, this is a trick for any kind of function space to function space learning that's very powerful, and it most of the time ends up looking like some kind of integral. We'll talk about that a bit more later in this talk, and then also in part 4. Does anyone have any questions on this overall architecture? Okay, so we formulated this on paper, very nice, but now we're going to put it into a computer. We have a finite collection of measurements. We actually need to decide how we're going to compute this integral and make some choices. So the first option results in what's called the graph neural operator, which was the first version of this architecture that appeared, presented. And the idea is that we'll use a Monte Carlo approximation of the integral. So we'll say we have a couple of measurement points. They were maybe chosen uniformly at random from the domain, maybe not, but we'll pretend that they were. And so we'll just take a straightforward average then of the integrand here. Is the simplest kind of approximation of an integral we could possibly do. If the kernel that we have is somewhat localized, which is to say that it decays off its diagonal. By the diagonal, I mean if you put the same point into the kernel twice, then we can only, that would mean that the values of this are very, very small unless x and zi are close together. And so how you end up at the graph neural operator is, let's say this kernel only has support for fixed x in a ball of some small radius around x. I can look at all of the measurement points that I have, and I can form an edge to those other measurement points that are close enough. Then you can implement this procedure for approximating the integral with a message passing algorithm on this graph that I formed based on the kernel. What's nice about doing this is that if I get a new measurement point, or I lose a measurement point, I throw it into the graph, I make a new edge, I take away the edge, and I still run the same thing. Of course, these might give you ever so slightly different answers, but the idea, and again, the overarching philosophy of this way of approaching the problem, is that all of these different discretizations are approximating the same thing. The more measurement points I have, the more accurate this will be, but it is still well-defined with respect to different collections of measurement points, and it doesn't change the parameters that I've used to learn this kernel function. This might be somewhat expensive if we have a large number of measurement points, because we're going to need to effectively compute this big kernel matrix of all the points with each other, especially if it isn't super localized. But then there's a whole bag of tricks for computing kernel matrices like this. You can use Nystrom or low rank approximations. There is an extension of the original graph neural operator paper to kind of multi-pole discretizations where you kind of zoom out on varying scales to approximate the behavior overall. And lots of other tricks in the literature coming from different areas, but anytime you want to approximate some big kernel matrix between a lot of points, you do have options if that becomes large, because the naive scaling here is going to be quadratic in the number of points that you have. So a lot of measurement points might become infeasible at some point, but you can use random feature expansions, low rank approximations. You have options if you want to do it this way. So there is another option to compute this integral kernel transformation that will lead us to the Fourier neural operator. And it's based on the observation that if we restrict ourselves to a stationary kernel, we have the beautiful results about convolutions and Fourier transforms, which is that the Fourier transform takes integral convolutions to pointwise multiplications in the frequency domain. And so because of this, we don't even have to learn this kernel directly. We can just learn its Fourier transform. And what we'll do is we'll learn its components in the frequency domain. This just becomes a standard multiplication, very, very efficient to implement. And then we'll take the inverse Fourier transform to get the answer of this full transformation. So we'll just learn the Fourier transform of K directly in frequency space. We'll just learn, the coefficients of its Fourier modes. And then if our measurement points are nice enough, we'll discuss what that means. We can use the fast Fourier transform to do, the moving to the frequency domain and back, which is really, really fast, as the name suggests. So this is a very efficient way to implement this kernel transform, and it ends up actually working really well and being pretty powerful. So as you said, they're very fast. You don't have to worry about these approximations for computing the kernel matrix like you do in the graph version. What's also really nice is if you end up having measurements that are sampled at a more fine resolution, you still can take the Fourier transform. Now you have access to some higher modes, but you don't necessarily need to use them. You can still use exactly the same kernel that you had from before, and then recover a finer grid than you trained on. In this sense, you can do one-shot super resolution, which is a heavily advertised feature of this method, which is very cool. And also, again, compared to the graph neural operator version, there's no computational cost for not having a kernel which is concentrated along its diagonal. In the graph neural operator version, if the kernel sort of sees everything in the domain and doesn't start getting small outside of neighborhoods of points, that really increases the computation time. But because we're using the Fourier transform, these sort of global relationships don't incur any sort of extra cost. And so here is a diagram of how one of these layers would work for the Fourier case. We'll have the input function to this layer. We'll take its Fourier transform. We'll hit it with some matrix of frequencies, which represents the Fourier transform of the kernel. And then we'll undo the Fourier transform with the inverse transform to get back to the physical space. Meanwhile, we have this pointwise linear transformation that's acting on the input. And in this sense, this actually looks a lot like a residual sort of architecture, like some kind of ResNet, where you're sort of going through frequency space for your nonlinear component inside of the pointwise nonlinearity, of course. And as many of you might be familiar with, these kinds of architectures end up being very, very powerful. So people who have worked on this architecture do give some universality results again, similar to the DeepONet. The method of proof is a bit different. The statement ultimately looks a bit different as well. So because we're using the Fourier transform, there is some subtlety about being on periodic domains here if we want to have, countable spectra. These papers do give some details about the existence of periodic extensions of your input function to periodic domains. So in theory, it always is, under reasonable assumptions possible to do this. And also the approximation theoretic results are given in terms of norms on Sobolev spaces. Things become very nice. For those of you who might not be familiar, Sobolev spaces are spaces of functions where you know that they have derivatives which exist in a suitable sense, and that those derivatives are sufficiently well behaved and integrable. So the first Sobolev space would be like a function that has a first derivative and its first derivative is in L2. In these function spaces, you can say things about how the Fourier transforms of these functions are behaved. And it means that they decay at certain rates. This makes a lot of things very easy. So for the Fourier neural operators, a lot of the results are stated in terms of norms on these function spaces, because it's what the theory kind of allows you to do more easily. But the spirit of the result is more or less the same. We're restricting ourselves to compact subsets because it makes these theorems easier to prove, though you can generalize them to measurable operators instead by the usual tricks of approximating them from the inside with compact things. And additionally, there are other universality results for the broader class of neural operators, not necessarily using the Fourier transform. And in this paper, actually, they give the results in terms of some more general norms on the function spaces. These proofs are somewhat involved, but main point of this being that we started by being inspired from deep learning and saying, let's have a layered architecture, which is linear, nonlinear, alternating. We wanted to use this kernel because it gave us a richer class of transformations that would exist on function spaces. And ultimately, this idea worked. It is sufficiently powerful to approximate any kind of operator that we would potentially be interested in under reasonable assumptions. There's one question. So the learned kernel is positive definite. So the question was, aren't there some specific constraints that also need to be imposed on the Fourier transform of K so the learned kernel is positive definite? I don't think that there is a requirement in general that that kernel be positive definite. I'm not sure if there's somewhere that states otherwise, but what I have seen so far does not put that requirement. If you did want your kernel to be positive definite, then you likely would need to make some assumptions. But I don't think in general that that is required. Any other questions? Okay, so now just some comments on organizing training data sets for Fourier neural operators. Typically, if we're going to be using the fast Fourier transform, we're going to want our measurement locations for the input and the output to be on somewhat regular grids. So in this case, a single training example would be this grid of input function locations, the associated function values there, and then we have the grid of output locations and the associated function values there. And an interesting thing about this architecture is because we're using the inverse, we're taking a Fourier transform and then taking the inverse Fourier transform, a single forward pass of the model is always going to give you the full grid. You don't have to query the full grid, implementation wise, and we'll see, examples of how this works in code coming up. But computing the output of the model will always compute the full grid for you. But as I referred to before, you can train on a single resolution and then make your mesh finer or less fine, and the model will still run and the parameters won't change at all. Another question here. Oh, this is a comment saying that the Fourier kernel is positive definite, so Mercer's theorem can be used. So that's for the kernel of the Fourier transform itself. I think I want to clarify something, that there's the kernel that is involved when we take the Fourier transform of something. But this is not necessarily a Fourier kernel itself. This is an arbitrary kernel that we would like to learn to represent a linear transformation of this part of the architecture. Okay, so this is just an application highlight. So this was from NVIDIA, I believe. Oops. And this was for modeling climate simulation for predicting the path of a hurricane using, a grid of data over the surface of the Earth. And we do see some pretty, impressive prediction. They have here, you'll see as the globe kind of swings around, it'll compare it to the NOAA forecast. We see their simulation is in the purple kind of contours, and the forecast that the I guess government agency otherwise uses is in the white cone, and they end up getting pretty good. I guess the ground truth is then the kind of colors that you see there. Try watching that one more time. But this is starting to be deployed for real applications and is giving, some pretty cool performance. So we do expect to see this kind of model and other similar models to really be increasingly used for real applications. Just the minor drawback is that the two grids that we use for the inputs and the outputs do need to be the same because we're going through the Fourier transform, but the resolutions of those two can change from example to example. There are extensions of the fast Fourier transform where you don't have to be on a regular grid. Most available implementations of it so far do require you to be on a regular grid, but there are some that are coming out that let you change to more complicated geometries. The other drawback, and we'll see some examples of this in part 4, is that it does not always have the best robustness against noisy corruptions of the input. And that is also because we're using the Fourier transform for this case. Okay, so that concludes the description of the model. Next up, we'll show some implementations of this in JAX. And then we'll move on to part 4, where we'll describe a new model that we have been working on and some interesting applications of operator learning methods in general. Are there any questions, I guess, before we move on? I can stop sharing here.
Okay, so I will start. There are any questions, and then you can address them. Okay, so the Fourier neural operators. Okay, so this is a general sketch of the Fourier neural operator that's modified for purposes of notational consistency. So in the paper, you will see this is denoted by A, and the input and the output is denoted by U. So because before we were denoted the input by U and the output by S, we changed it so that is consistent. So again, we have the same setup. So we have some X inputs and some Y output correlations. We have some input and output function pairs, right? And we want to learn an operator using them, right? So as we said, the Fourier neural operator is an iterative architecture, like V0, V1 to V big T, right? And then this can be split in three parts, right? The V0, which is essentially something that lifts the last dimension, like the channel dimension, and then there is iteratively applying this neural operator layers. And the last dimension essentially projects back the channel dimension to the dimension of your output, right? So the first and the third part, they're doing by some local transformation. For example, some shallow fully connected layer. They are using also convolutional layers, but anyway, we will use fully connected layers here. Okay, so let's see how the step 2 works. Okay, so step 2 is we define this V tap plus 1, which is essentially what Jacob described, which is this linear layer with a nonlinearity. And K can be defined as some integral operator, which then we take the Fourier transform of that, we do the Fourier trick. So what I'm trying to explain here is when we go to the implementation and we'll see how the spectral convolution is constructed, you will see something that's not essentially familiar. There is some matrix vector multiplications. And so I'm trying to motivate why these matrix vector multiplications are why is this implemented like that in the first place? And this comes essentially from the math, right? From properties of the Fourier transform. So thus far, this is what Jacob described. You have this Fourier transform of kappa, and then Fourier transform of V. And then this kappa is essentially This is parameterized by, this is called R phi, which is parameterized by some complex parameters, right? So if you go to the paper and section 3 and 4, you will see that you can actually consider some properties of the fast Fourier transform, and then this essentially reduces to some matrix vector multiplications with the corners of R, right? So this is actually a very, very cool trick. You can check that out in their paper. I highly recommend it. So now what are we going to do next is we will again explain the problem that we are trying to solve, which is again the same flow through porous medium. Okay, so the setup is exactly the same as it was before. There is nothing different, right? There is again the Darcy law, again the same boundary condition, the same dimensionality, the input and the output domain coincide. There are scalar fields, right? So exactly the same. Everything is exactly the same. Okay, so for this particular tutorial, we will need a deeper introduction to stacks, right? So let's start by importing these necessary libraries. Okay, okay, so this is some. Now, as we talked before, you have this R matrix, which is complex. It's complex value, and this is trainable, right? You learn these parameters from your data. That means that you need to go to change some parts of the up-down optimizer to properly use it. Okay, so this is how the optimization is done, how the update step is done, the gradient-based optimization. And when you have like complex parameters, then you can have these Wirtingen derivatives, and they look like that. Okay, in the case of JAX, when you take the derivatives of the loss function with respect to these complex parameters, you get this derivative where is this minus here, right? And obviously we don't want this minus here, because minus here, minus here. No, this will probably don't work as it was supposed to. So what we need to do is take the conjugate of that, or is the plus, right? So this is the first thing that we need to do. The second thing that we need to do is the atom optimizer computes the squared norm of a gradient by squaring its elements, right? This, in the complex case, will not give us the norm that we are supposed to get, right? It will only works for real parameters, right? Real gradients. So, okay, so then what we can do is go to the optimizers, the stacks optimizer source code, take this complex atom, right? And then take the conjugate here. And then instead of having g squared right here, you just need to multiply the conjugate g by g, right? And then take the real part of that. Now, if you see, there is some optimizer decorator here. This optimizer decorator, what it does is essentially, it takes your optimizer and makes it work for pi trees. So if you remember for part 1, we said that there are these structures called pi trees. There are a list of lists, and then the basic structures of parameters in JAX. So this is how you save parameters, right? In this big list of dictionaries and all these kind of trees. Okay, so step 1, fix the atom optimizer to be complex atom, right? Again, we need to handle batches. So this is exactly the same code as it was before. We have this structure that we provide batches, and then it chooses the mini batches for us during training. And this is done again in this JAX kind of way, that we provide some initial key, and then they start splitting the key such that each time we get something different. Okay, so let's go and talk about stacks. All right, so if you remember, we talked about this stack serial. This stack serial library is essentially, it takes a lot of, you provide layers, right? And then we take this, it takes those layers that they are defined as pure functions and stacks them together as operations that they are done one after the other, serially, right? So in the Fourier neural operator, we have an initial lifting of the dimensions, right? And then iteratively, we need to do this nonlinearity, and then this WV, which is this transformation plus the kernel, right? So we have a lot of things going on. and then we can take all those things, put them in stacks layers, and then stack them together such that we can apply all of them serially, like you see here, like a dense, and then this V iterative, iterative update, right? And then this is what we would like to do: stack all this operation one after the other to make them act iteratively. Okay. Right. So as we said before, each of these functions will be defined by an initialization function and an apply function. Okay. So now we need to understand how we can define this pure function that you see here, dense, FNO, block2D, and all of the others, such that we can have this kind of structure. So whatever goes out of the first one goes to the second one, and then goes to the third one, and so on and so forth. Okay, so let's start by talking about the dense layer. Oh, something that I forgot. Again, another property that we would like to have is that we would like to not care about the batch dimension, right? So we would like to have -1 here, which means that you will vectorize on the batch dimension. Okay. So let's go talk about the dense layer, which is a very simple implementation of a fully connected layer. So what do we have here? We have, again, an initialization function that is essentially creating the parameters, as we've seen in tutorial 1. And the other thing that we need is this apply function, which is essentially the forward pass, like it applies the transformation. Okay, this is the first thing that we need. The second thing that we need is a permutation layer. In the permutation layer, such that we permute the channel and the spatial dimensions, such that we apply the fast Fourier transform to the spatial dimensions, right? And then the permutation layer is, again, will be built in a stacks pure kind of manner. Okay, so if you see here in the initialization, we have two things. This provides us with two outputs. One will be the parameters. The other will be the output shape. So the output shape of the first layer would be the input shape to the second layer. The output shape of the second layer will be the input shape to the third layer, and so on and so forth. And this is how we will have this construction that stacks together layers serially, one after the other. So you need to be careful that when you have this this series of transformation, whatever is the output of one goes as the input to the other, the shapes, right? Because this input shape here that you will see in every initialization function, what it does is essentially that initialize the weights, right? So this provides you with the shape of the parameters. Okay, so this permute function does not have any weights. Now, this is the part that we started talking at the start, right? About the convolutions in the Fourier space, right? So what we have done here, we will define a spectrum convolution. Okay, so in order to do that, we will have, again, an initialization function. What is this initialization function? This initialization function will essentially be some complex matrices, right? If you read the paper, you will see that essentially in the 2D convolution, this 2D convolution, you need two matrices, right? That represents the two corners of this R matrix. So we will define two matrices, one W1 and one W2. And then this initialization function will provide us again with these two complex pitris with parameters, so pitris with complex parameters, and then an output shape. Okay, so the apply function, we will perform the real fast Fourier transformation to the input, so the real fast Fourier transformation to V, and then it will perform these matrix multiplications with R, and then it will provide us the inverse real Fourier transform. Okay, so because there is some conjugate symmetry here, this is why you have the half of the domain. So don't be alarmed by that. All right. So the next thing that we need to do is add this part, this WVT. So we have computed out of this part here, we have computed this part, and now we compute this part, the WVT. So in order to compute the WVT, we will use a dense layer, the one that we have defined above. So what do we have here? We have a dense layer, we have and times the VT, and then what we have, the second one is this inverse of the Fourier transform that we have computed up here, right? So we created a new block, the FNO block, that will provide us with this exact thing. So this will be constructed by two parts. One that computes this, which is, we talked about that above, and one that will compute this. Again, we need an initialization function and an apply function. The initialization function will provide us with the parameters of this WV transformation, and the parameters of this Fourier, inverse Fourier, right? So the output shape now should be it's like what we discussed before. Now this output shape will be the input shape to the next layer that is stacked serially, right? And then at this point we essentially do this summation of these two parts, and this is the second thing that we want. Okay, with these three simple blocks, the dense, the permutation, and then FNO block 2D, we will build the whole architecture, right? By stacking them one after the other. Next, let's talk about the loss function. The loss function is the same as it was before, right? In the Fourier neural operators, they're using, in their paper, they're using this loss function, which is, we call it relative L2 error loss, which is essentially a way, as we said before, this is a structured way to put weights in each loss function component. That's pretty much the idea, to avoid, overfitting at specific frequencies, something like that. Okay, so, and this is how we define it, right? As we did before. And now we go to the large model class. Okay, so if you remember, again, we need to define a layer, and this layer is a composition of layers, it's a composition of transformations. A composition of transformations, the one that we talked about above. So these three transformations, dense, permutation, and FNO2 block 2D, put them serially together to get one layer, that's a big layer one, which is a layer of serial transformation. Okay, and then again, this will provide us with a init function and an apply function. Again, we do this, we define it, we get the parameters, we do this unravel pi tree, because we take this pi tree, we unravel it, right? And then we will use that to store our parameters such that we don't need to retrain. Okay, and then we define again the optimizer, the complex Adam in the way that we talked about the real Adam optimizer, let's call it, which is, again, we need an initialization parameter, an update rule, an update function, initialization function, update function, and one function that will provide us with the parameters, right, the state of the optimizer. Again, we have some loss. We have this L2 error such that we can compute the L2 error as we train, so that we see how well we do, right? Then we have this step, right? This function, which is pretty much updates the state of the optimizer at its point in the training loop, and then we have the training loop, and then this function to count parameters, right? This is pretty much the idea. Okay, so again, we have these model definitions, and we have we load the data. We have some definitions here, how many, the number of input-output function pairs, the batch size, how many iterations we will train, and all that. So here we also compute the grid, right? And then, oh, something that I forgot. This R matrix, right? That with the matrix with the complex value parameters, right? So if you see here, we will create a grid, the input grid, like the spatial grid, which is the same as the output grid, And then we will concatenate it with the input function samples. And this is the input to our model. So one might think that in order to perform this Fourier trick, we said that the kernel is stationary and there is no connection to the input function, right? But now we are taking the input function in this R. So it's actually very interesting because the input functions now are like the R is parameterized with respect to the input function. There are not some argument. You can read it in the paper. This is very interesting. Anyway, so the other thing that we need to do is take our data, right, and make them like JAX device arrays, and then put them in the data generation to handle the batches. And this is how we define our model, right? Dense, permutation, blocks, 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 activations, then permutation, again, one dense to lift the dimension even more, and then GELU, and then project it back to the dimension of your output. Okay, so this is how they define it in their paper, their code they have in GitHub. This is the way that we did it. So here we define the model, we count the parameters, and then we train the model. Okay, so if you see this trains in 6 minutes or 7 minutes, something like that, which is more than the DeepONet that trains in 1 minute, but it has some increased accuracy. It's like pretty 0.3% or something, right? And then what we do is essentially that we fetch the parameters, we do like a one-shot prediction for all realization for all the whole resolution, right? And then we compute the error, right? This is how we compute the error, and we will see the mean, the standard deviation, the minimum, and the maximum, right? And then the other thing that you can do is pretty much, save the model parameters such that you can use them for, don't train the next time. You can use them such that you don't need to do that. So that's the end of the third tutorial. Yeah, thank you.
All right, I think we have a few minutes for questions, either on the method side or on the implementation side. It seems that everything was super clear. All right, I don't see any questions coming in for part 3. We have a slightly longer, part 4 is a little longer, so perhaps we could take the break now and then resume at 3:30 to start part 4. And we'll stay online if questions come up. Feel free to just type them and we'll try to answer. So quick 10-minute break and we'll be back at 3:30.
Thank you.
Thank you.
Okay, I guess we can get started.
Yeah, we can start with part 4, which will be on more advanced topics. Jacob will go over some recent work that we've done on an attention-based architecture inspired by all the success of the transformer models in natural language processing. And then we'll show some results, some applications of physics-informed operator learning, and hopefully we'll have some time for a more general discussion in the end. So Jacob, you can take it over.
Thank you. Make sure I'm not muted. I'm not muted. Okay. So the next segment of the tutorial is going to be about a third operator learning architecture that we recently have derived along with our collaborators at Penn, which we have titled LOCA, which stands for Learning Operators with Coupled Attention. And so the starting point of this is perhaps, the first paper that introduced this idea of an attention mechanism. This was in the context of learning to translate a sentence from one language to a sentence in another language. The idea is that we have some input sentence, which we have suggestively called U here, from, we have T sub U words to a sentence in a different language, S1 to ST. So each of these represents some word in a language. And so the way this, proposed architecture worked was you first would map your input sentence to a set of features, which we're calling V here. And then for every location in the output sentence, you would construct a so-called context vector that was specific to that index in the output sentence to help form a probability distribution over words to select one from that output sentence. And the main idea that we're going to adopt here is the creation of this context vector. And specifically, it's formed as an average over these input features with a distribution that depends on where you are in the output location. So the analogy that I'll speak about again, but kind of to hold in your mind as we go forward, is every index of the output sentence is kind of like a query of our output function. And we'll examine how we form these distributions associated to the various queries of the output by which to average some input features. So here's a nice big diagram for a visual representation of how this worked in the original paper. We have our input sentence. Associated to this, we make some input features. These again are, in this scenario, indexed by the indices of the input sentence up to T sub U. And then we form these so-called attention weights. And attention weights are sort of used interchangeably with this idea of a distribution over the input features, but notice that it depends on the index of the location in the output sentence. TS is the final index for the output, TU is the final index for the input. So we get one distribution for each place we can query in the output. For each one of these locations, we then form the so-called context vector by using this distribution formed from the attention weights to average over our input features. And then this vector is thrown into another component of the model that would help you form a probability distribution over words to then select the word in the output sentence. There are some details that are being brushed under the rug here, but for our purposes, the main point of inspiration we have from this model is this location-dependent averaging procedure. So to reiterate, this happens depending where you are in the output. It's formed as a very simple average over a discrete set like this. And we also can represent it, if you prefer this form, in this kind of diagram. So what this means here is, think about this as the indices for the output sentence, which later will correspond to a domain for the output function. This is the space that the input sequence would live in. So we have T sub U elements of this sequence. Each of them is some d-dimensional vector. And then for a given location that we want to query in the output sentence and a particular sequence in this space, the sequence gets mapped to some collection of features, and the location gets mapped to a point in the simplex on T sub U elements. Once we have a distribution in this space and a feature vector here, these then get averaged together to form the context vector. Checking for questions. So inspired by this kind of mechanism, we're going to take this and apply this to the operator learning problem that we've talked about before. So in this case, U is our input function, which again is a function from some domain, let's say calligraphic X to R to the du. This will get mapped to a collection of n features. N is going to be integer that, or a whole number that can vary with the architecture. And each one of those features will have dimension ds. And we're going to do this because this is the dimension of the output that we eventually want. Once we have this collection of features, depending on the point of the output distribution that we want to query, we'll form a probability distribution depending on that location. We'll actually form ds different probability distributions so that we can average over the rows of this big feature matrix. And so this is totally analogous to what we showed before in terms of the creation of the context vector. We'll use this notation, the expectation of these features with respect to the probability distributions that we create, to mean we're going to average over the rows of these features with each distribution contained, one for every copy of the simplex here. And so we could write it this way, that it's a sum of a bunch of component-wise products of the columns of V. So the average is going over the rows, so we sum all of the columns together weighted by the weights given by this phi function. And again, we have this similar kind of looking diagram, but now we've replaced it with the objects from our operator learning problem. So whereas before this represented the set of indices for the output sentence, now it represents the domain of queries we use for our output function. Whereas this before was the space that an input sentence would live in, this is now the space that our input function lives in. It's a function from calligraphic X to R to the du. And because we're considering functions potentially in the output side that are vector valued, we've augmented this by allowing not multiple probability distributions, one for each coordinate of that output dimension. So a single query point will be mapped to ds copies of the simplex. That's one probability distribution for each coordinate of the target space of the output function. We'll get a finite set of features from our input function, and then we'll do this averaging procedure to get our proposed answer. And this will form the basis of our operator learning architecture. So now there are some decisions to be made. In particular, we need to decide what are these features going to be, what are these probability distributions going to be, how are we going to make them and allow them to depend, in this case, on the output query location y. So the simplest thing that we always can do, and this happens fairly often, is if we want to make a probability distribution, a map into the set of probability distributions, we can first just take any old map into r to the n by ds, because we need this many numbers. And then we compose it with our favorite function that will normalize into the simplex and give us a probability distribution, such as the softmax. And we're going to do this across the rows of the output of this function so that we get ds of them. We're not going to normalize across every entry of a single element in here. We will just do it across the rows. And we know that if we use a sufficiently rich class of functions G, sometimes these are called score functions. And that means it's a function sort of pre-normalization that then turns into a probability distribution. If we have a rich enough class of functions for the scores, then we know we'll be able to build any probability distribution in this way. However, if that's the case, then we're requiring this score function to learn all of the relations possible between the probability distributions at different query points. So going back to the kind of high-level formulation of the model, you'll notice that for a given input, the value of the output function at two different locations is entirely determined by how their associated probability distributions are formed. This part of the model is exactly the same no matter where I want to query the output function. So if there are relations that we want to enforce, smoothness, continuity, any kind of regularity or correlation structure between the values of the output function, it has to come from the way that we build these probability distributions. And if we do it in the simplest way possible by taking a single score function and then normalizing it, we're hoping that this function g, some kind of whatever your favorite parameterized class of functions is in a neural network, is itself going to learn these relationships. So we ask, is there a way that we can allow the model to learn these relationships explicitly, as opposed to just hoping that the parameters of this function itself will learn it from the data? And so the answer to this question that we came up with is what we call the kernel-coupled attention. The way that this works is we'll take our score function, the same one as before, that's our sort of, proposal score for forming these probability distributions, but then we'll couple it to itself with a kernel transformation. This will allow us to form a new score function, which we'll call g tilde. And then this in turn will be normalized to form our probability distribution for that particular output query. And if we give this kernel a parameter, then we would allow it to learn potentially any kind of structure that would be present in correlations between the values of the output function. So a couple very simple examples of this are, if this was some kind of Gaussian kernel, this would be performing a local smoothing, which would be enforcing the output function to have a certain smoothness to it. On the other hand, if it was some kind of Gaussian kernel with a very, very small length scale or bandwidth, then this is only forcing the score function to be averaged at a certain point with its very, very close neighbors, and as such isn't necessarily making the function that smooth over longer length scales, and it could be allowed to vary more widely. By different choices of the kernel K, we also could have then everything in between. There could be a periodic structure. We could have potentially anisotropic structures where things in certain regions of the query domain are very highly correlated. Maybe they're correlated across big gaps. It doesn't have to be so regular. And by parameterizing the kernel with a somewhat flexible architecture, we potentially have more room in the model to learn these structures and not just rely on a simple architecture for this function g to do so. We also need to make a choice now for the input feature encoding v. We're going to give just a very high-level description of this for now and return to it a bit later in the talk. But ideally, as we talked about for the other two methods, the goal of this is to be flexible with the kinds of discrete measurements we have for the input function. But we also still want this to be sufficiently flexible so that we can learn different feature maps that might work well with the model. So one idea to construct such a map is, let's first find some kind of fixed feature extraction of our input function, which we'll call calligraphic D here. And then we'll take those features and push it through something that is very, very expressive. For example, some universal class of functions, some set of neural networks. And if we choose a good initial feature map and a sufficiently rich class of functions for the second component, we can then approximate lots of different potential encodings V. We'll return to this a bit later in the talk, but this is the high-level structure for what this functional will look like. So here's a picture of the overview of the model. We see on the left, and so this is, as an example, let's say we're mapping one scalar field over the Earth to another. For example, we have a temperature field, and we would like to predict the pressure from that field. So we have our input field here. This gets mapped to some features, which are then shuffled around. We learn some interesting transformation of that to some informative features. And then on the query side, we have our points that we might want to know the value of the output function at. They each have their own individual proposed score function, which then are mixed together by this kernel transformation, hopefully enforcing some correlations between them in the output, which will form then a true probability distribution over each of them that then together with these features will be averaged to get the value of the output function at a certain point. And a single expression for the overall evaluation of the model is given here, where this is exactly what we had written before, coming from the inspiration of the context vector and the Badenow attention, but now replaced with our kernel-coupled attention mechanism, where we have the normalization of the kind of convolved version of our proposed score. Are there any questions here before we move forward?
quick question. How do you compute these integrals at the end?
Yes, we will talk about that. Okay, I'll continue on. So we'll talk about some computational considerations, but first we're going to talk a bit about what kind of universality guarantees we can get from this kind of architecture. And so similar to what we had spoke about earlier in the day, our starting point actually is, again, this theorem of Chen and Chen, which gives a universality guarantee for an architecture that looks like this, which, based on the way we wrote it, does look somewhat similar to our architecture, but with a few notable differences. What we're going to do is start with this architecture of Chen and Chen, and with a couple of steps, mold it into our model and show that each one of those steps does not destroy the universality guarantee. So we're going to do that according to the following procedure. This is, we might consider a vectorized version of the Chen and Chen architecture, where that proof would apply, coordinate-wise. We need to have a normalized version of these weights of the G's, the part that takes the query, because we're going to average over them instead. So we need to make sure that that using normalized functions here does not break anything. And then additionally, we have this kernel coupling step. We want to make sure that that also does not break anything. If we can go through those two steps without destroying the universality, then we actually know that this form of the model will be universal as well. And so we are able to show that. The first step is that if we instead restrict ourselves to a normalized version of these functions, we still have the same universality guarantee as before. And there's a somewhat explicit procedure for how you show this, is that the Chen and Chen theorem gives you an existence proof of an operator of this form that's epsilon close to the true operator under, again, the assumptions of compactness and continuity, which can be relaxed if you would like. And then we modify those functions so that they have this normalization property. In doing so, and this goes back to a question that was asked earlier, we do end up with a kind of overcomplete basis. So this is a somewhat crude argument, but for the purposes of existence, it does show that there will be a function of this form that can approximate any continuous operator, on these compact sets. The second thing that we need to show is now, if we use this kernel coupling mechanism to form our probability distributions, this also will not result in any loss of expressive power of the model. So to phrase this in a different way, we need to say that any probability distribution, potentially on DS copies of the simplex, but just talking about one of them for now, can be written in this way if G itself is coming from a universal class of functions. So we're thinking of G as being sufficiently expressive to approximate any score function that we would want, which then under normalization would give us a probability distribution. But we're not using G, we're using the smoothed version of G, this kind of kernel coupled version of its values. And so one way to show that this still can generate any probability distribution is to show that it can generate any score function, which is to say that functions of this form, if G comes from some universal class, are also still dense in the space of continuous functions. So obviously we shouldn't expect this to be true all the time. You could come up with a form of this kernel that would make everything collapse to a point, or to lie on some finite dimensional subspace. So certainly we're going to need some kind of conditions on the kernel that we use if we're going to hope that this is true at all. And it turns out one answer to this question is by drawing a connection to the theory of reproducing kernel Hilbert spaces. The short answer is that if this kernel is positive definite, symmetric, and is associated with a universal RKHS, then we're good. The connection here comes from the fact that what we're asking is, this is an integral operator that we're using to act on our proposed score function. What we want to say is that if we start with a dense subset of this domain here, of this integral operator, and we look at the image of that dense subset of the domain space, that the image is itself still dense. The connection to the theory of reproducing kernel Hilbert spaces is that the square root of this operator, if we look at the square root, which we know exists because we're saying that this kernel is positive definite, and symmetry helps. The image of the square root of this operator is exactly the RKHS associated with the kernel K. If the kernel K is universal, we know that that RKHS is dense in the space of all possible score functions. And so that connection then allows us to reason through pushing in a dense subset of the domain through the square root of this operator twice effectively to get a single application of this operator. And then we can see that that is also dense. So ultimately, the condition here is that we have a kernel that defines a universal reproducing kernel Hilbert space. And that will ensure that there is no loss of expressive power by doing this kernel coupling step. Animations are off here, but so now we arrive at the question that Nahir had asked before, which shows up in every one of these talks, which is everything is nice on paper. We have discrete measurements. We need to actually compute things in a computer. How are we going to do this? So the two simplest options that we have are one, the Monte Carlo approach, where we have the points that we have, we treat them all equally and use the simple kind of sum approximation of this integral. And the other option is that we can use a quadrature method. So these both potentially have their advantages and disadvantages. Quadratures work very, very well if the dimension of the space calligraphic Y is low. Thankfully, in a lot of applications in physical domains, this will be the case. I want to predict the flow of a fluid through a two-dimensional domain. This is very reasonable. It can be done in a small number of computations. The Monte Carlo approach has the benefit of we can reuse the measurement points as sort of nodes in the approximation of the integral, but there will be then potentially quadratic cost associated with doing this as in the graph neural operator, if you'll recall from the talk earlier. And then, as usual, there's a whole bag of tricks for approximating then these big kernel matrices that computationally end up being computed, low rank approximations, random feature expansions, you name it. An option that we didn't consider, but one certainly could, is if you use a stationary kernel, you could use this Fourier trick as they do in the Fourier neural operator as well. Lastly, we need to still have a few more decisions to make about the choice of this feature encoding. I left it a bit vague before saying, well, there'll be a fixed feature map, and then we'll have functions G from some very expressive class. We're going to consider two options now. The first is we could use as this initial part some kind of spectral projection. So take a nice basis of functions of L2 on this space calligraphic X because it's compact. This is still, we're not really losing anything by all of a sudden now we're talking about L2 instead of the space of continuous functions with the supremum norm. This does still make sense. These could be Fourier modes potentially, or whatever your favorite basis of functions is, and this could be very domain or situation dependent. And then we'll push those projections through some universal class of functions. So what's nice about doing projections in the L2 sense of this form is, as I alluded to, I guess in the previous talk, if you want things that are relatively discretization invariant, integrals are usually a great place to start because different discretizations just give you different ways of approximating the same integral. So this is why the Fourier neural operator works well with grids of varying resolution, is because you're still effectively just computing projections onto Fourier modes. You're performing these like L2 looking inner products, and that is still able to be approximated if you have different measurement schemes, and they're all trying to point at the same answer. Of course, there'll be little differences depending on the actual locations you use, but it's not like you need to retrain anything or that the procedure just isn't even well defined anymore. We could also use something like a wavelet basis here. Wavelets have very nice properties and have seen a lot of success in certain signal processing applications. And so is this going to be expressive enough to approximate any kind of functional from our space of input functions to Rn? And so the answer is, under some assumptions, of course, yes. What we require is uniform convergence of the spectral expansion of our input function u along this basis, which is a bit easier to happen again when everything is compact. But this means that we're not going to, if we use enough of these projections, we use enough basis vectors with then that second component, which is a universal class of functions, we'll be able to approximate any functional that we want, which is required, sort of going all the way back to the original Chen and Chen idea of there is some functional that gives us the correct answer. And so we want to make sure that our architecture is sufficiently rich to approximate that. However, in practice, we end up using a different feature encoder. And this is the so-called scattering transform, which was introduced by Stefan Malat and John Bruna, I guess in the beginning of the 2010s. And this is built off of some wavelet transforms, but with a bit of a different structure. So for those of you who are not familiar, wavelet transforms typically take some kind of mother wavelet. It'll be some function that looks like this, and you consider various dilations of it. And if you're in more than one dimension, you also can consider rotations of it. And so rotations and dilations of this mother wavelet will be represented by some parameter lambda, where J represents a scale factor and R represents a rotation from some discrete rotation group. And so we can form kind of transformed versions of this mother wavelet by considering different values of the scale factor J and this rotation R. And what we'll do is we'll consider what we'll call a path of a couple different of these lambdas. So I'll consider a certain scale and a certain rotation first, and then I'll have a sequence of these that are potentially different. And what I'll do to my input function is first I'll convolve it with the dilated and rotated wavelet corresponding to that first parameter. And then I'm going to take a complex modulus of that signal. And then I'll convolve it with another wavelet, potentially a different scale factor and a different rotation. And I'll repeat this some number of times at some depth that will be pre-specified. And I'll finish it off with a low-pass filter. And if we consider all possible paths with a fixed depth where the scales and the rotations come from some finite set, we get what are known as the scattering coefficients. And this is the output of the scattering transform. This ends up having some really, really nice properties sort of by design. In particular, it's relatively robust to small deformations and noisy corruptions of the input. Here's a diagrammatic representation of it. So this is our input function. Every time you see a black dot coming out of the side, it means you hit it with the low pass filter, this function phi. And you iteratively kind of go down this tree. So we take the first, we take just the low pass filter with it, that gives us something. And then we have, in this case, 3 different scale and rotation combinations. We do each one of those, composed, nonlinearity, low pass filter, shoot it off, and then ultimately down here, these black dots are the outputs of this transformation. It's based on fast Fourier transforms and conjugate mirror filters, these techniques from signal processing. So this is not a computationally horrible thing to do. And what we find is that it works really, really well in practice. It works better than any kind of spectral approach that we saw before, or even pointwise measurements for that input feature encoder. The one caveat to this is we no longer can use the universality result that we had before for the spectral version of the input encoder. Part of the reason is the inverse problem for the scattering transform is somewhat non-trivial. And in fact, it does not have the best continuity properties. You can have 2 input functions whose scattering transforms are close, but are a bounded distance away in LP. So for proving universality, this means that the approach that we used before very, very likely will not work. But it is still a bit of an open problem whether there's a version of it a version of that kind of statement that could be used with the scattering transform. But as I said, at the end of the day, practically this gives the best performance. So we chose to use it and kind of run with it and see what we can do. So to recap, overall, this was the form of the model. We have our kernel coupled attention component here with which we average our features. There are parameters in the kernel, there's parameters in the score function. There are no parameters in this fixed feature part, which for most of our applications is a scattering transform, but the function that we apply to it does have some parameters. This is typically some kind of neural network. I think we're missing a slide here. Maybe we're not. So to compare it to the two architectures we looked at before, first the DeepONets, we can actually recover the DeepONet architecture from our model in a similar procedure to as we try to reduce it to the Chen and Chen architecture due to the connection between those two. We would have to remove this normalization component and the kernel coupling. And we also, in the feature encoding, instead of using the scattering transform or this kind of spectral expansion as the first component, would consider that fixed feature part calligraphic D as a collection of delta functionals that just give you pointwise measurements. If you do these two things, you effectively have a DeepONet. The comparison to neural operators is most easily seen by some work which actually connects DeepONets and neural operators together. There's kind of, you could start from either one of these sides and get to the other via some particular choices. This paper here gives a pretty explicit explanation of how you can start with a neural operator, and under some choices you make its kernel separable. You have a certain lifting and projection procedure with the linear components, gives you something that looks like a DeepONet. So transitively, we can connect ourselves to neural operators through that connection. There's another interesting connection to neural operators, which is the scattering transform itself we can view as a certain kind of neural operator with particular choices of filters and a particular choice of nonlinearity. To be specific, the scattering transform is a neural operator where those kernels are given by wavelets, and the pointwise nonlinearity is given by a complex modulus. And there's no pointwise linear components. Also, it has fixed weights, but we think of this as a bunch of neural operators together because each path of those wavelet parameters would correspond to a different neural operator with fixed weights. So that component of the model is like you have a bunch of fixed neural operators all stacked on each other, and you look at their outputs. Okay, I think now I will hand it over to George to talk about some experiments that we run and some comparisons to the other operator learning methods.
Oh, yes, thank you, Jacob. Okay, so, right. So before going into comparisons and experiments, I would like to first talk about the way that we make the comparisons, right? So, and this is, for operating learning methods, we would like to have like three properties. One, data efficiency, which means that they should be able to provide small median error and error spreads when trained to a small number of labeled data. The second is robustness, which means that when you input some noise in the testing or both training and testing dataset, you should not, your accuracy should not deteriorate a lot. Okay, so the third property is generalization, which means that you would like to be able to have accurate predictions when you have some distribution shift, or the nature of the task changes in some way. Okay, so now for the comparison metrics, as we've seen in the code tutorials, our comparison metric will be some relative L to error for each individual input-output function pair, right? We will compute that separately. And then we will construct an error vector for which then we will compute some statistics, such as median, percentiles, outliers, right? Also, to have fair comparisons, we have pretty much comparable or close number of trainable parameters, and we train like the workload times pretty much the same. It's very close. So how do we sample? How do we create our input samples, right? So how we create a training data set? As we've seen, we have like the U function and the S, right? So a pair of input-output function. For the U function, we will take some M available points, right? So as many as we have, and then for S, we will choose some P out of big M points randomly. So these points are sampled differently for each realization, and then we will say that we have a percentage of the whole label available labels. So if we say like we have P, which is 128 out of 1024, this is 12.5%. So some percentages are not that, rounded. So we will round to the nearest half integer. We have percentages like that. Okay. So we have 5 examples that we have tested this method. One is some simple antiderivative operator, the Darcy flow that we have seen in the tutorial, and then the mechanical lemnist. So the mechanical lemnist is some lemnist digit that you consider them to be some heterogeneous block materials, such that you can apply some equibiaxial extension. So you displace the left, right, up and bottom the same displacement, and then this starts, the displacement changes, right? So the difficulty in this thing is that wherever you see a digit which is a different color, the Young modulus is like 2 orders of magnitude larger, which means that you have some very big difference in stiffness, right? So we will use these examples to essentially prove our points, right? We will not present all the results in this presentation, but you can see them in the paper if you like. Okay, so about data efficiency. So data efficiency means that we will operate in the small data regime, so small label data. So for its input-output pair of functions, in the output we will have a percentage of the label data. Okay, and we will train with that. So we will start with a very small percentage, and then we will go up to the whole data, the whole label data. Okay, so now we need to care for 2 things. The first thing is obviously the median error, but the second thing is the presence of outliers, which means the worst case scenario in the our worst case scenario prediction in the particular data set, which is very important because it's the worst we can do. Okay, so also we will have this kernel coupled attention mechanism. We will have it in the model and remove it and see how does this affect the efficiency of the model in the small data regime. Okay, so this is for the Darcy flow, and then we start with 1.5% of the data set and go up to 100. As you can see, this model can very, very quickly get up to an accuracy, very good median error, a very small error spread that, let's say 6% is better than the other method with close to 100%. Okay. So the effect of the kernel coupling, this is very important because we can have 1.5% of the data set. Instead of having 1,000 output pairs, we can have, let's say 200, and then run the example, and then you will see that this will blow up. It's unstable, right? And then your mean error will be something like 46%, right? Instead of 1%. So the kernel coupling provides stability in the small data regime, and also we believe that makes this method work well in the small data regime. So second property, robustness. How we will assess robustness? We will create 3 scenarios, 3 noise scenarios. One noise scenario with no noise. Clean simulation data for training, clean simulation data for testing. Second scenario, clean simulation data for training, noise data for testing. Third scenario, noise data for training, noise data for testing. Now we will present a new error metric. And this error metric will be the percentage increase in mean error between the clean and the noise data scenarios, right? It's not accuracy, it's percentage increase. So we will train the clean and then use it as baseline and then input noise and see how does this noise affect the accuracy by its percentage increase from the baseline. Okay. Also, obviously, also the presence of outliers. We will use 7% of the available output function measurement as training labels, and then the Gaussian noise is sampled from what you see in the bottom. Okay, and now you see the examples, the results. The results are clean to clean, noisy, clean to noisy, and noisy to noisy. Obviously, the displacement is a vector, right? So you have one displacement on the horizontal and one on the vertical axis. So that's why we have like 2 bar plots. And what you see here on the red is local, blue is DeepOnet, green is FNO. Okay, so you see that in the clean case, the FNO is very accurate, right? But then we input the noise and the error explodes pretty much. So it's like close to 2000% increase, right? From clean. So if you add noise in the tested data, and this has to do with Fourier transform, right? And they are unstable deformations. So then if you train noise to noisy, you see also some increased percentage of decrease in accuracy, right? But Loca in both cases have the lowest of that. So again, it's like not accuracy, but percentage increase. Okay. And then generalization. So to test generalization, we'll have two examples. The first example in generalization would be something like a distribution C, right? So you will have the antiderivative operator, which is something simple. And then in the antiderivative operator, you will have a forcing term that will be sampled for the Gaussian process prior, okay? And then we will change the length scale. So what happens here is that we will run for 9 length scales. Okay, so we will train for 0.1 length scale here. We will test in 0.1. We will do that 10 times and then take the mean error of each time, and then statistics. Okay, so then we will train in 0.2, test in 0.1, and so on and so forth, right? To see this, what happens in this distribution C. Right? Then you see that the local method reaches a plateau, while the other methods are constantly increasing the error. The second thing in the generalization, the second example in the generalization is some climate modeling example. So these black box operator learning methods are useful because essentially you can map to different parameters that there might be no equation, right? So we have some input function with some temperature over the Earth, right? It's daily temperature over the Earth. And then on the other hand, we have pressure, right? Surface air temperature, surface air pressure. Okay, we have 5 years spawn of that for training, 5 years for testing. So now the training problem is a little bit different. Our input-output function pairs are daily temperature and pressure. No, temperature input, pressure prediction. So what we do is use this from 2000 to 2005 for training, and 2005 to 2010 for testing. Right? This is, you can find this data available online. Right? You can see in the paper for the link. And this is pretty much what we get. So you see that Loca is essentially providing a very small median error and also a small error spread. While the DeepONet is very close in the median error, but the outliers are, they're going very much larger. And then the FNO has some, it's not that accurate, but the error spread is not that big. Okay, and then here I will stop, give it back to Paris.
Thank you, George. Perhaps since I'll be sort of switching gears and bringing up a slightly different aspect, maybe we can take a few minutes for questions, if there are any, on the Loca architecture and the results that George and Jacob just presented. We'll have also more time in the end, but I think it might be a good point here to focus on the Loca architecture. All right, I don't see any questions coming up. Okay, there is one. How does Loca cope with input locations that are not fixed across batches? Maybe I can take it myself, and maybe if I'm wrong, Jacob or George can correct me. In theory, Loca can handle input locations that are different different number of input locations, different number of input sensors, let's say, and also locations. In practice, in all the simulation results that we just showed, we had the same number of measurements per example and the same locations just to facilitate a fair comparison with DeepONet and FNOs that have this requirement of regular grids on one side and then fixed number of sensors on the other side. That being said, in order to accommodate different number of measurements and locations of measurements in LOCA, while in theory, the method should support it, the implementation can get kind of messy if you want to enable that feature. So our current code, I think, does not support it, but that would be just a matter of implementation and extension, which might make the coding a bit more messy, but in principle, that should be doable.
Yeah, to expand on that, it's, I think, similar to the case of the Fourier neural operator, where that the inputs are handled effectively by integrating them against various filters. So in the case of the Fourier neural operator, they're against Fourier modes. With the scattering transform, they're being integrated against wavelets. So it is well defined with respect to measurements that are not necessarily always the same, but then you would need to do more work on the implementation side to actually compute those, and then additionally, in a computationally reasonable fashion. Whereas for the kind of standard version of the DeepONet, it is relying on those inputs very much architecture-wise being at those locations.
Yeah, the thing is that implementation-wise, we wanted to have some, on one hand, flexible architecture, but on the other hand, robust to input noise and deformations and all that. So we chose the scattering transform. Right. So the scattering transform is a little bit tricky to, have a varying input resolution. It's a little bit tricky. It's not undoable, but we haven't implemented.
There's another question on why do you think the DeepONet has so many outliers compared to LOCA?
Oh, okay. So I would say that there is no mechanism such that they can somehow find this underlying structure between, between different samples, right? So as in LOCA is this kernel coupling attention mechanism. In the neural operators, there is this learnable kernel. In both cases, it's something that learns from the underlying structure. I think that's my opinion. Jacob, what do you think?
We have not tested what I'm about to say specifically, but it is possible that the presence of the kind of normalization step also might make things a bit more stable.
And the encoder is, I think that if the DeepONet had some kind of encoder, it would be much less outliers, I think. And I have an explanation.
Another aspect is that many of those experiments are sort of pushed to the small data regime because we really want to highlight the importance of this kernel coupling in terms of modeling correlations in the output functions. So if you don't have explicitly a mechanism like that in your model in the small data regime, it's sort of expected that you might suffer in terms of accuracy. So that's potentially another reason why LOCA outperforms the DeepONet in those experiments. All right, any more questions before we move on? All right, perhaps I can continue from here, and then we can also have some time towards the end. Or see, there's one more. Can any of these be reverse engineered for applications to NLP tasks, since this is the primary source of inspiration?
Oh, that's a good question. So application-wise, there should be some changes in the code because NLP models are very large. So I think that you should apply some kind of no, this attention mechanism should be in a way approximate, right? With something that scales linearly. I don't know if you are asking from a math perspective or implementation perspective, but from implementation perspective, we should change some stuff. Like So
I think the
steps.
question relates to the fact that, going back to NLP, now we're back in the discrete setting where you have, the inputs are sequences of words, for instance. So I guess,
Oh, I see.
could we
So
view that type of problem in the operator setting and maybe use what we've learned to
okay,
introduce some
so from a method perspective.
So I think it is somewhat straightforward to at least try to apply this kind of architecture to that sort of problem. What you would do is the input domains of your input and output functions are no longer, open sets in RD. They're going to be discrete sets instead. But you could then carry out all of the computations analogously, kind of as I think to the point of the question is suggested by the sort of initial slides. You can kind of do everything the same if these were sequences by thinking about sequences as functions from discrete sets to some space of tokens or whatever. The kernel coupling step would, that integral would be replaced with the sum. You potentially wouldn't need to approximate it in the same way. And I believe all the steps could be carried out in a similar fashion. You might want to use a different input encoding. I don't know if the scattering transform necessarily is appropriate if you're talking about a signal like that instead as a sentence, but it is possible that you could try, or there would be some alternate architecture that would be more suited for language data.
All right, so let me move on to the last part of the presentation. Start by sharing the screen. And I'll actually take you back to this example we saw earlier with DeepONets, just to highlight some aspects that are common among all the methods that we presented, either local or DeepONet or Fourier neural operators. So going back to this example, we can remember, in this case, we use the DeepONet to learn the antiderivative operator from paired examples, from paired observations of the source term, the right-hand side of the ODE, and the resulting trajectory that we generated using some numerical solver. Now, there's a simple question one can ask. Do the predictions of the DeepONet at test time satisfy this ODE? So if I take the predicted trajectory of that my DeepONet has produced, I plug it into the ODE, will I get a zero residual? Is this equation satisfied? And it turns out that the answer is not really. So in other words, maybe we're not really learning this antiderivative operator that you see on the top hand of the slide. And this is just a very simple experiment that you can do. And in fact, it turns out there is some sensitivity with respect to what activation functions you're using in your DeepONet. It turns out that the ReLU tends to work a little better than the tanh in this case. But what you see here on the bottom figure is on the left-hand side, you have the prediction versus the exact solution of this problem. So you see that a DeepONet with the ReLU activation can give a reasonable approximation to a test trajectory. However, if you take that test trajectory, you plug it into the ODE and you take its first derivative, you compute ds dx, you would expect that should match with the right-hand side, which is u of x. But it turns out that if you compare that prediction with the exact u of x, you get this kind of, very wiggly plot on the right-hand side. So you have a residual that is definitely not zero. So on one hand, that indicates that the predictions of the DeepONet in this particular case, but I guess that could also extend to FNOs or LOCA, may not be, there's no mechanism that guarantees that those predictions are consistent with the underlying, let's say, physical law that generated the data. Obviously, this argument only makes sense to make in cases where indeed there is some underlying physical law and perhaps there's a set of equations that we know a priori. So it doesn't really apply, this argument does not apply to the general black box operator learning setting. But for this particular case, it seems like that the predictions of the DeepONet model are not, let's say, physically consistent according to this governing equation. Furthermore, another common feature, which we try to alleviate in part with LOCA by introducing this kernel coupling, is that all of those operator learning models, they do require large numbers of labeled examples for training. So both DeepONet and the FNO, perhaps LOCA to a lesser extent, but all of them require large data sets in the orders of thousands or tens of thousands of labeled examples. Again, for this ODE problem, that's not an issue, but if you think of more complex applications where the cost of generating a single example is high, it involves some expensive simulations or experiments, you can imagine that the application of those techniques might be prohibitive. So motivated by those drawbacks or limitations, one area that we've looked into was how could we actually impose some constraints in a soft manner during model training to encourage the output of DeepONets in this particular case to be consistent with the underlying set of equations. And of course, this is only applicable in the cases where we do have a set of equations that we know that our predictions should satisfy. And it turns out that there's a very simple trick one can do. And if you recall, the outputs produced by DeepONet are basically continuous trajectories. So they can be queried continuously at any given query location y. And therefore, that means they're also differentiable with respect to y. And we can actually use automatic differentiation in a very similar spirit that we use it to compute gradients of our loss function with respect to theta. We can also use it to compute gradients of the outputs with respect to those query coordinates y. And by doing so, this allows us to actually formulate things like a residual loss. So for instance, we can take the prediction of a DeepONet, plug it into an underlying PDE or ODE governing law, and compute the residual that tells us how faithfully the prediction of the DeepONet satisfies the given equation. So by doing so, we actually, essentially, we're introducing a regularization mechanism. So while training the DeepONet model, not only we will be minimizing this loss function that ensures that our model fits the observed output measurements correctly, but we can actually have an additional loss term, which we call the physics loss, which boils down into evaluating the outputs of our DeepONet model at a collection of Q spatial locations and try to enforce the residual of the underlying governing equation to be as small as possible in this location. So we just pick random locations in our computational domain, and then we try to make the predictions of our DeepONet model to be consistent with the underlying equations at those locations. For those of you familiar with the framework of physics-informed neural networks, this is basically the same idea here, extended to the operator learning setting. So now, essentially, we define basically a multitask learning problem, where at the same time, through these additional penalty constraints, we're encouraging the DeepONet model to produce outputs that fit the data, but also minimize the PD residual or satisfy underlying boundary or initial conditions. And at the end of the day, we just have this composite loss function. We'll minimize it via gradient descent, and now train a so-called physics-informed DeepONet model, which hopefully will fit the data, but also produce predictions that are consistent with the physics. Now, what are the advantages of doing so? Well, you can revisit this antiderivative example that I just showed you. And if you do include the constraint that this equation should be satisfied during model training, not only you can get much more accurate predictions, but you also can introduce a dramatic reduction in the amount of training data that is needed to train the DeepONet model. And this is basically because we're now leveraging prior information during model training, and that effectively will compensate for a much smaller size of training data. So for instance, if you want to achieve a target accuracy of 1%, a physics-informed model will be able to do so with a few hundreds of training examples, whereas a vanilla data-driven version will require a few thousand examples, so an order of magnitude difference. Same thing happens if you sort of fix your training data to be, let's say, 1,000 examples. With a physics-informed case, you get an accuracy that is an order of magnitude better than without those constraints. So there's immediate benefits in terms of accuracy and data efficiency by introducing those constraints, even in a soft manner. So they're not implicitly hard-coded in the architecture itself, but they're imposed during model training. Now, what was more surprising to us when we started working in this direction is this striking observation that in order to train those physics-informed DeepONet models, we don't even need to have measurements of the output functions inside the computational domain. In other words, having measurements that only reside at the boundaries of the domain would be sufficient for us to train those models, which is quite surprising because in this particular case, if somebody gives us a set of, let's say, ODEs or PDEs with a given initial or boundary condition that makes the problem well posed, then we do not need any additional data. We don't need to use some other numerical solver to generate a training set in order to train the DeepONet model. So only knowledge of initial and boundary conditions is actually enough to train the model by fitting those boundary conditions through this operator loss in conjunction with satisfying this physics laws that penalizes the residual of the ODE or the PDE. And this is really interesting because it basically removes the need for running any other simulations in order to generate training data sets. So the fact that you know the governing equations of the problem is enough to actually train this DeepONet model in the absence of paired input-output observations generated by numerical solvers. So that was quite of a striking observation. And again, for those of you familiar with PINs, physics-informed neural networks, that is basically a generalization of physics-informed neural networks that now allows us to use these DeepONet models to solve parametric differential equations. So essentially build a model that can solve those equations and can generalize across different scenarios that could correspond to different geometries, different initial, different boundary conditions, and so forth. So this is a summary. So recently we wrote a paper that appeared in Science Advances where we benchmarked this idea for solving very different classes of problems, starting from ODEs to reaction diffusion equations, to nonlinear hyperbolic equations, even to some, including the advection and the iconal equation. In all of these cases, the model is self-supervised, so no training data is provided other than the knowledge of the equation form and the associated boundary conditions. So this is the only information needed for training. And as you see here, this is an example for learning the solution of the Burgers, solution operator of the Burgers equation that maps any initial condition u of x to the full spatiotemporal solution of that system. So these are examples from the test data set. This is some sample initial condition. That would be the exact solution obtained by some Fourier spectral method, a classical numerical solver, and this is the predicted solution obtained by the trained DeepONet. And as you can imagine, now after training, the DeepONet is extremely fast to query, so we can actually solve in the order of 1,000 PDEs in less than 1 second on a single GPU, about 2 orders of magnitude savings in terms of compute time compared to a classical numerical solver for this case. So this is an exciting sort of development because this allows us now to build surrogate models for solving ODEs and PDEs, which are very, very fast to query at test time, and therefore we can actually use them for downstream tasks such as optimal control or design optimization or other type of studies that require the repetitive evaluation of some solver. So with that, let me move on to the next, to the final application I'd like to highlight, which is specifically in the context of optimal control problems, which can be formulated as PDE constraint optimization problems. So just to introduce some notation, in this setting, typically we want to minimize some cost functional and that cost functional needs to be minimized over the control input, so which is denoted by U. So U here will be continuous functions that denote control inputs. S will be the state, the associated state of the system, which is also a continuous function that should satisfy an underlying governing law. That could be an ODE or a PDE. So this operator epsilon here encapsulates the set of equations that need to be satisfied. And now the goal is to try to identify the optimal controller in some admissible set of functions such that this cost functional is minimized. And the idea here is we can train operator learning models to learn the map between input controls and the state of the system. Obviously, models such as the DeepONet are also differentiable, which then gives us a surrogate model that we can use to very, very quickly solve this constraint optimization problem, this PDE constraint optimization problem. And the interesting aspect here is that we're still operating in infinite dimensions. So the control functions are continuous, the states are continuous. So this is an infinite dimensional constraint optimization problem. And the main advantage of using operator learning is really to bypass the cost of solving the governing equations, which appear here in the constraint, which could be an ODE or a PD, and in practice, that could be something that is expensive to solve. The way we have done that so far, it's a very preliminary approach, but we've tackled such problems by taking a two-step approach, whereas in step one, first we will train a physics-informed operator learning model, such as a DeepONet, as we saw earlier. So in a self-supervised manner, we're given the equation and the boundary conditions, we're given some distributions of possible, a distribution over possible controls, and then we learn the map from control inputs to the associated PD solution. And once we have the surrogate, notice that the surrogate now is differentiable with respect to theta. We can optimize any parameters alpha that parameterize our controllers very, very cheaply and very fast, because now we have this differentiable surrogate that we can plug into the evaluation of our cost functional and then use gradient-based optimization to obtain some locally optimal configuration for the controller. Notice here that all the gradients of the DeepONet loss with respect to its parameters, the gradients of the cost functional with respect to the control parameters, or even the gradients of the state with respect to space and time coordinates are all computed through automatic differentiation. So, all right, so this is just an overview of the idea. Let me just give you a highlight application, which involves the optimization of a circular object subject to Stokes flow. So this is a two-dimensional fluid flow problem where you have flow coming from the left of this domain. There's an obstacle here, and then the flow exits on the right-hand side, and there's two wall boundaries on the top and the bottom. This is a steady state problem described by the so-called Stokes equations, which are denoted here. Here, U denotes the fluid velocity and P denotes the fluid pressure, subject to some appropriate boundary conditions. And now the goal here is, can we identify the shape, the geometry of this obstacle that minimizes the dissipated energy of the fluid, or that minimizes the drag force that is the fluid exerts on this object. So for that, we have to assume some type of parameterization or some type of form for this obstacle boundary, denoted here as d gamma, partial gamma. And for simplicity here, we'll assume a parameterization that corresponds to a family of circles and ellipsoids. Later on, that can be generalized, but just for simplicity and illustration purposes, we'll just confine ourselves to basically identifying the best ellipsoid shape that minimizes the drag of this obstacle. As I mentioned, this is a two-step process, the way we have approached this problem so far. So step number one requires us to train a physics-informed DeepONet to learn the solution operator that maps any given obstacle geometry to the associated solution of the Stokes PDE. So for that, we have to employ a DeepONet that takes a representation of the object geometry, and then as an output, it produces the full spatial solution for the U velocity, the V velocity, and the pressure in a way that the Stokes equation is satisfied. Once we have that, then we can readily go to step number two, that requires us to basically identify the best obstacle geometry that minimizes this cost functional. This cost functional describes the dissipated energy of the fluid, the first three terms, subject to some volume constraints and subject to a constraint that the barycenter of that object needs to be fixed at some coordinate point, gamma 0. Again, once we have a trained surrogate, then this step two, the second problem, becomes trivial to solve because we have a very, very quick way to evaluate this cost functional. Not only that, now the cost functional is differentiable with respect to gamma because our DeepONet model is differentiable with respect to the input geometry. And therefore, we can actually employ gradient-based optimization techniques to solve this in almost real time. Obviously, there's the offline cost we need to pay for training the DeepONet, but once this is done, the actual shape optimization problem can be solved in real time. And these are the results. And in fact, it took us more time to produce the animation than it took to actually solve the optimization problem. You see here, we start from some initial configuration that looks like a circle, and then the model is optimized to obtain an ellipsoid, which actually this is what we expect from theory for the optimal shape to look like. And also, this is the associated cost functional for the dissipated energy that is minimized within a few hundred of iterations using a simple gradient descent algorithm. Finally, I'll just highlight, we've tried different examples here. I'm presenting results for the Stokes case, but you can also see that the benefits versus a conventional finite element type of approach for solving the same problem. Finite element approaches would require you to formulate the adjoint system of equations in order to be able to get gradients of your cost functional with respect to the control inputs. So you will have to solve forward and adjoint PDEs at the same time in order to solve this problem. And obviously, a trained DeepONet is much, much faster in solving a single PDE. And then putting it together, obviously, you get some significant speedups in terms of tackling this PDE constraint optimization task. That sort of highlights basically the merits of the physics-informed constraints in terms of data efficiency, but also the fact that then once you have those surrogates, they are differentiable with respect to their inputs, so you can use them for downstream tasks such as control and design optimization very conveniently. So with that, we have some time that we have reserved for the last 20 minutes of the tutorial, and I'd like to open the floor for discussion, questions. We have listed some topics here that we thought it'd be interesting to discuss in terms of what are the open challenges, open questions in this area. So let me keep sharing my screen. I'll just maybe keep it, sorry. Not in full screen mode, but I'll just put that slide up there. We can get the discussion going. So perhaps we can start with any questions on the last part of the tutorial, and then maybe we can jump into the discussion.
Thank you, Paris. I may want to start with a question since you have the bullet point adversarial robustness. Yeah, what are your thoughts on that? What is adversarial robustness in this context? And if you can comment on that.
Yeah, that's a great point. And actually, we had a discussion right before the session with Jacob that brought up this point. So perhaps I'll defer to Jacob. But I guess it is really the notion of adversarial robustness that we think in the classical finite-dimensional supervised learning setting that needs to be formulated for these operator learning models as well. And it's sort of an open ground that we're not aware of any existing works. But I think Jacob can provide some more thoughts on this.
Yeah, I think the kind of starting point for thinking about it is, even in the finite dimensional case, there's a lot to understand about how adversarial robustness works, how you could try to encourage it and, defend against, the main idea being small perturbations of the input totally breaking the model that you have. In high dimensional spaces, we know that these seem to be abundant, but then, moving from high dimensional to infinite dimensional spaces is then a bit of a shift as well. And it'd be interesting to think of this kind of in both directions. One, what changes, if anything, as we go to function spaces from high dimensional finite vector spaces and characterizing the presence of, small perturbations that can really horribly change the performance of models like this. And on the other hand, in the limit of very, very high dimensions, as we see a lot of, the data from traditional machine learning living in, are there any insights from formulating this problem in infinite dimensions that then, can transfer back to the high finite dimensional case as well?
So in the presentation, so you mentioned about enforcing, basically having soft constraints. So my question is that, are there scenarios that actually we can enforce them as a hard constraint and actually satisfy them after training?
Yeah, I think
some sort of regularization.
Yeah, that is a great point. ideally, this is what we would like to do in many scenarios, to actually have those constraints to be part of the architecture, and the architecture implicitly satisfies certain properties. I think really that depends on the type of constraints. So, for instance, simple symmetry constraints with respect to certain symmetry groups can be sort of incorporated, and one can design appropriate architectures and define convolutions over graphs to sort of impose those implicitly. But moving to more complex constraints, things like PDEs in complex scenarios like fluid dynamics, where the symmetry groups may not be a priori fully known, it might be very hard to actually make those constraints part of the architecture. Ideally, that's what we'd like to do, but it could get quite challenging in some of the more complex cases. And of course, the fact that we're taking the easy way out and we're using those soft type of constraints in this setting introduces some complexity in the optimization problem, because now we have multiple loss functions, and then there's interactions between them, and it becomes more of a deep learning task that you have to tune weights between different terms. We've done a lot of work to try to analyze this type of problems from an optimization standpoint, characterize the convergence rate of different loss terms, and come up with ways to balance their interaction. So I think there's a lot of work that could be done in this direction. And that's sort of the unfortunate problem that we get by taking this easy way out and imposing the constraints in a soft manner. That often leads to an optimization problem that might be hard to solve.
And I guess the choice of the regularization parameter can have a drastic impact on the results.
Absolutely. It absolutely does. And in fact, in many cases, you have to even, think of schedule. It's not even a fixed parameter, but you have to sort of anneal it through the optimization. So we've done some work to try to come up with, let's say, systematic ways of doing so that have some justification from a mathematics point of view. But indeed, it becomes quite tricky. And in fact, I should make the comment that for the people that are familiar with physics-informed neural networks, this framework basically inherits all the advantages and limitations. So if there is a PDE that you can solve with pins, then I'm fairly confident that you can use this physics-informed DeepONet model to tackle the parametric setting, where now you can solve the same equation over a range of initial boundary conditions or geometries. At the same time, there exists a very large class of problems that pins fails to solve, and that relates to all the difficulties associated with the optimization problem, and those difficulties again are inherited in this setting. So it might be really hard to tackle complex PDEs where whose solution may exhibit, chaotic behavior, is sensitive to initial conditions, and might require really high accuracy in order to be approximated. So accuracy is one of the as we mentioned here, is one of the elephants in the room, because the best you can hope for these type of models is, okay, you get an error of about 1% or 0.1%, but for some applications that may not be good enough. For instance, when you're modeling chaotic dynamics, that small error can very quickly throw you take you to the wrong direction.
Actually, that was my next question. Your thoughts about learning chaotic dynamics. I asked this question from George yesterday as well.
Mm-hmm. Yeah, I think there is two sides of this here. One is, I guess, the setting that I described here is that we are given the governing equations, and we want to use those tools to emulate their solution, to predict the trajectories given the equation. In this case, accuracy plays an important role, because if your predictions are not accurate and you're in a chaotic regime, then you're your trajectories will deviate really, really fast. And yeah, it's an open question, and pins and DeepONets currently suffer from this. We have some ideas, we've made some progress, we have some ongoing work that we're about to finalize that shows some promise in this direction, but still you cannot really compete against classical solvers for ODs or PDs, which have a very good control of how those errors propagate. Now, the other question, there's this other angle to this question on learning chaotic systems where all you observe is, chaotic time series. You don't have an underlying equation and you want to extract the dynamics from that. That's sort of like the inverse problem, which might be a little easier than the forward prediction problem, but obviously, yeah, there's a lot of challenges when we go to the chaotic side of things. Mm-hmm. So I guess the way we decided to group some of those bullets, some of them are more related to theory aspects. We briefly discussed the adversarial robustness, but although for plain neural nets that approximate functions, currently we have some understanding of what are their implicit biases under gradient descent and their representation biases. This understanding is lacking in this operator learning setting. So that is sort of an open question to better understand what are the implicit biases of these models and how those affect the generalization. Also, what is not well understood so far is, what is the sample complexity, how much data do we need? And the notion of data efficiency here is quite different because here we have two things to consider: the number of function pairs in our training data set, so the number of examples, but then within each function pair, there's a number of measurements we have for the input or the output functions. So data efficiency is a really important aspect for these methods, or a property for these methods to possess, but it's still kind of poorly understood. How much data do we need relative to the complexity of a given problem? So that's an area that definitely we need some work to understand this better. And that also relates to the data acquisition problem, in which we always have a finite budget when it comes to expensive simulations or experiments, and maybe not all examples are equally informative. So how do we really go about selecting and generating those training data sets? So that's a question of experimental design. And obviously there's a lot of work done in the finite dimensional setting, but moving to these operator learning problems, that's another area that is wide open for people to think about. Any questions from the audience? So next question by Antoine. Any thoughts on generalizability in the presence of bifurcations? I can take an initial thought on that. And I think there might be some hope for generalizability in this setting, as long as the training data set contains examples that reflect the bifurcation. So we have examples before and after the bifurcation. So the model has been exposed to those two different regimes during training. I'm not sure how accurate the predictions will be at the transition, near the transition from one state from before or after the bifurcation. But I think it would be really crucial to have examples in the training data set that reflect both cases. Now, in the physics-informed setting, one would hope that if the underlying ODE or PDE constraints are satisfied accurately, those should encode the physical structure, and you may hope to be able to capture bifurcations. But obviously, it's a tricky, it's a challenging question. I don't have a lot of practical experience on this, so I'm speculating. I don't know if Jacob or Georgie has any more experience on this or comments.
Yeah, I'm not sure about that, to be honest. I don't have experience with that.
That's a good question, and that's something actually that shouldn't be too hard to test in a canonical benchmark. My hope is that if examples in the training set reflect the system state before and after the bifurcation, we should be able to provide some decent predictions. But yeah, that's just my hope. Any more questions from the audience? We have a few minutes left.
One more question.
Is there a participation list of the attendees? I think that's more.
Yeah, that's administrative question.
Yeah, question for Christina. Okay.
Yeah.
Maybe just to summarize, I just point you again to the repository we created. We'll be posting, we have already posted links to the slides and code. So we have uploaded the PDF with the slides and the Python notebooks with the coding tutorials. We will also be linking the videos when those become available. There's also links for you to download the training data. A small disclaimer for anyone who wants to use these codes for commercial purposes. Unfortunately, this is prohibited because George Kaniadakis' group at Brown, they filed a patent for the DeepONet model. And in fact, in their patent, they even claim that the FNO is a subcase of the DeepONet. So they've been a little bit protective of those techniques, and commercial use is not currently is not allowed. But for any questions, or if you find any of the material interesting, or if you find any mistakes in our codes, please get in touch. We have our emails here. We'd love to hear from you, any feedback, or if you would like to apply those techniques to your own work and you need help in doing so, we're happy to connect with you and discuss more.
Well, thank you so much, Paris, George, and Jacob, for the excellent practicum as well as very exciting results at the end. So this concludes our this year's workshop on winter schools. So we will post the videos, the ones that we have, of course, on the event website. So please stay tuned, and I hope everyone has enjoyed. And I guess if there's no questions, so I guess have a very good weekend, everyone. And thank you so much.
Yep,
Thank you very much
here for hosting us, and thanks for everyone tuning in. And of course, many thanks to George and Jacob. They did a great job.
Thank you.
Thank you very much.
Take care, everyone.
Take care.
Hope to see you soon. Bye-bye.